Hello, everyone, and welcome to our second instalment in the Nuclear Science Webcast series, brought to you by the National Nuclear Laboratory, the UK's National Lab for Nuclear Fission. And I'm really excited to join you today as the host. My name is Dr. Sophie Cooper. I am a chemical modeller at the National Nuclear Lab, and what that means is I spend a lot of my time modeling the chemistry of novel systems in the industry on an atomistic scale. So I'm really excited today to join the audience and take that step back and look at how fuels play their part in various reactor technologies and how those reactors play a key role in decarbonisation of various industries, from electricity production to a few of the novel systems that we'll be looking at. And to do so, we have a panel of 4 speakers that are all experts in the area. And I would very much like to welcome them to introduce themselves. So we're going to start off with Dave.
Good afternoon, everyone. So my name's Dave Goddard. I'm a senior fellow at National Nuclear Laboratory, based at our Preston facility, which is on the Springfield site. I've been involved in the manufacture and characterization of nuclear fuels for about 30 years now, looking at a whole range of different technologies. I'm particularly interested at the moment around the advances in fuels and next generation fuels for the future reactors that we might have in the UK.
Thank you, Dave. And next, if David, you could introduce yourself.
Yes, good afternoon, everybody. I'm David Ease. I'm Chief Technical Officer based on the same site as Dave, and we're very much focused on making fuel innovative for the future.
Thank you, David. And next, on to Kathy.
Hello, everyone. My pleasure to be here. My name is Cathy Thirier. I'm a technical manager for advanced fuel and materials here in the Canadian nuclear site, the other side of the ocean. I'm pleased to be part of this panel. I've been studying nuclear fuel for the last few decades, actually, mostly in fuel fabrication, characterization, testing, and currently focusing on leading programs here in Canada to look at advanced fuel for the next reactor to be deployed in Canada soon. Thank you.
Thank you, Kathy. And last but not least, Phyllis.
Hello, everyone. I'm Phyllis Makurunje, and I'm a research Banker University at the Nuclear Futures Institute. I look at of manufacturing nuclear fuel and trying to improve existing methods as well. And this is both for fuels that we use in space reactors here on Earth, and also looking at opportunities in space. And it's great to know.
Thank you, Phyllis. So just a bit of an explanation of how today is going to run. We have 2 broad themes that we want to talk about. So firstly, I guess, why you should be excited about nuclear fuel, so the applications of different reactor technologies. And then secondly, I guess, the how. So talking more about the design and manufacturing of fuel and how that plays a part into the fuels we have and potentially in the future. To do that, we are really keen to know what your questions and thoughts are. So you should see the opportunity in your on your screen to ask some questions in a text box. We'll try and get through as many of those as possible in the next hour. We also are really keen to know your opinions on a few topics and to make sure you're still listening. So do be aware they're going to pop up on your screen 2, well, 3 questions throughout the session. So before we hit on questions, just one quick disclaimer I want to say is that the views of ours are their own and are not attributed to NNL. With that in mind then, I'm going to start off with questions of my own that I've come up with before we get through all our great questions from our audience. So to kick us off then, my first one's to Dave. So we know globally that the demand for electricity is increasing. In fact, we expect it to double by 2050. And also, a lot of our energy, about 20% of our energy use is electricity, so a lot isn't. How does fueling the future relate to that?
Yeah, Thanks, Sophie. That's quite a broad question and not an easy one to answer in a very short time. But clearly, nuclear has a role in the future. I think speaking for from a UK perspective here, the government policy is very much that nuclear needs to contribute to our decarbonisation targets, and part of that is about continuing to provide that baseload electricity generation that is essentially keeping the lights on in the country. But at the same time, we need to be starting to think about future applications of nuclear and going beyond just electricity generation and trying to look at decarbonising some other energy uses. So, for example, using nuclear reactors to generate high heat that could be used by industrial processes, or using heat to produce hydrogen or synthetic aviation fuels, a whole host of other applications. And of course, these different applications likely need reactors or slightly different types of reactors to perform those applications. And from a fuels perspective, we have to keep pace with this, because the fuel that goes into a reactor is very specific to the type of reactor. As we move to different types of reactors, we have to advance and develop the fuels that will go and fuel them in the future.
Thanks, Dave. So I guess just adding on that point of all of us have seen our energy bills increase in the last few years. So we all are starting to realise that energy security is important. Do you think that nuclear is a realistic solution to help reduce domestic fuel bills?
Yeah, I think that's a really valid observation in how our domestic fuel bills have fluctuated over the last couple of years. Has been a real reflection of vulnerabilities in energy security. So nuclear obviously can play an important role in that. And we, if we look at the UK again specifically, we have always had domestic fuel manufacture supplying the fuels for our own reactors. And I think that's a really important ambition to keep and to pursue into the future. So whatever reactors we deploy, having that domestic supply throughout the front end of the fuel cycle. So that includes enrichment, deconversion, and the manufacture of the fuel itself. Having that security is really important for us.
Thank you, Dave. So my next question is for David. So as Dave just touched on there, we've got a range of different reactors that we might call upon, but different reactor types will need different fuels. Could you expand on that?
Sure, yeah, so I think just for clarity, as you open with the National Lab for Fission, so we talk about fission reactors here. So the one thing that makes all of them common is they have a fissionable isotope in them, which generally is uranium-235. So that's there in uranium. They just mentioned enrichment there. There's different variations of that. That presence of fissile material is key. So that is, as in a reactor, we then need something to sort of keep it all in place, which generally is something metallic. Some reactors use zirconium, some use stainless steel. So if we look in the UK, we've got two types of reactor operator. We've got a pressure water reactor and advanced gas cooled reactors. They both share the same uranium dioxide fuel in pellets. They look very similar, slightly different in diameter. One has stainless steel cladding, and there's zirconium. So you can see there that with that sort of type of reactor, there are similarities too. But then when we start to look to the few other types of reactor, and there's various developed strands of them would be like molten salt fuel, which could actually look quite a bit different to what we're familiar with now, where you have typically uranium dioxide based fuel and some sort of metallic cladding, and how you sort of get the heat out of the reactor, because that's actually part of the reason for the design of the fuel cell inside the reactor. And actually to be able to utilize that, you've got to get the heat out, where a lot of the technology comes in the design of fuel and how it's done such that you can make use of the heat that you generated to generate electricity used for other things.
Thank you, David. My next question is for Kathy. So we've just spoken about a few different types of fuels there with David. What fuels have you worked on in the past, and what are the key differences between them?
Yes, absolutely. So I was mostly with uranium dioxide fuel, which is a conventional type of fuel that was and David. Also at different enrichment level, meaning different percentage of fissile material in them, especially when I was leading the effort here in Canadian Nuclear Lab for refueling a research reactor, which use up to 19.75% fissile material. So that was a uranium type of fuel that I work on, more traditional. And over the last 5-8 years now, we are in Canadian Nuclear Labs looking at increasing our knowledge in the development and deployment of advanced type of reactor using advanced fuel. So it was mentioned molten salt fuels and as well as a tree structural isotropic type of fuel, which is a tiny little kernel covered with different layers, which is the used fuel for high temperature gas cooled reactor. And so what key differences between them? Well, the application. Some of them are more robust for high temperature operation and the high burn up, so amount of energy that we can get out of them.
Thank you, Kathy. So the last one there is for Phyllis. So we've just spoke about the fact that typically we use uranium dioxide fuels, but moving to more novel ones like molten salts. So fuels need to be designed for different scenarios. Could you tell us more about some future advancements?
Thanks, Sophie. So as an industry, we are in a continuous cycle to keep innovating and improving on existing fuels indeed. And the buzzword these days has been accident-tolerant fuels. And these are fuels that can perform in normal operations in a reactor, but they can also perform in abnormal situations where they face maybe extreme conditions, and this is when it's referred to as accident scenarios. But what is important is that having a fuel that can perform in good conditions and not so good conditions is very important. Having a fuel that is robust and resilient to such whether they're expected or unexpected conditions is very important. It's critical. And some of the things, one parameter that the industry is looking at is thermal conductivity. That is, how does the fuel handle the temperatures that it has within it, the heat inside, say, a fuel pellet. And it is important that having high thermal conductivity is great, because it means that the fuel can drive the heat out and pass it on to the coolant. So that is really important, because you don't want things to get really hot when the fuel is operating, because water is difficult to handle. And also just structural robustness is key. Just improving on that is important. So improving on the resilience of the fuel to interacting with the coolant in the reactor. That is also very important, because we want the fuel, whether it's in a reactor that uses water, gas, molten salt, or metal cooled, it has to be resilient to interacting, to have this side interactions or unwanted interactions with the coolant. So those are some of the design considerations that we look at in when designing the fuels.
Thank you. That was really interesting. I think that's a great opportunity whilst we're waiting for some questions from our audience. Hopefully that sparks some ideas to move on to a question to our audience. So you should all be shortly seeing, if you're not already, the question that is, what do you think is the most exciting application of future nuclear fuel? So we've got three options here. So obviously, as we've already spoken about, producing electricity is the main method of using nuclear energy at present. So increasing the supply of low carbon electricity, or are you more excited by the idea of supplying heat for other industrial applications? So a lot of chemical industries need high temperature from desalination to producing synthetic fuels and oils, and the potential of hydrogen production as a new fuel as well? Or is the idea of powering space missions what you find most exciting? As we wait for those responses to come through. Right, so interestingly, we do have the idea of having low carbon electricity from nuclear is the most favourite. I don't know if anyone in our panel wants to touch on that and just reiterate the importance. No, okay. Well, oh, Dave, you're on
Yeah,
mute.
sorry. I think yeah, we should respond to the poll, and I think it's perhaps as you might expect, really, that what we currently do very well is seen as quite important into the future, and I think the sort of condition I put around that is that, like any industry, the nuclear fuel industry should always look to improve and develop. It's about not being standing still. So that is where, and Phyllis talked a little bit about the interest around accident tolerance, or sometimes people call them advanced technology fuels. It's those you might call incremental developments in how we manufacture fuels that has either some economic benefit to the reactor operator, it has some beneficial performance in a condition. So, what are those advancements? And some of the things we're aware of, or we've been working on, for example, is by putting a coating on the zirconium cladding tubes. So, for a light water reactor, zirconium is used as the cladding material, and that has some vulnerabilities in certain accident scenarios. So how we make the potential reaction at high temperatures with zirconium and steam less of a problem. And one way to do that is to apply a thin coating to the surface, which forms a barrier to that reaction. So that's something that's being developed by fuel vendors and organisations, universities, national labs are helping with that development. And we're seeing sort of some really significant progress in that area, that those coated cladding tubes could well come into operation in our next generation fleet of light water reactors as soon as the start of the next decade. So there are lots of things that we can do with our own, supporting baseload supply, the current generation and next generation of light water reactors and small modular reactors that will benefit from advances in nuclear fuel.
Thanks, Dave. I just want to ask Kathy, in terms of supplying heat for industrial applications, are there any differing novel applications that you see in the Canadian National Lab?
Yeah, absolutely. Canada is a very large country. We have population very spread across, and one of the objectives also for using off-grid small modular reactors, so advanced type of technology, is to provide low emission source of energy in remote community in the north. So that is a very specific application for our country, as well as we are fortunate to have a very large natural resources with a lot of mining. Canada is the first supplier of uranium in the world. And also from other natural resources here, minerals and so on. And one of the key applications as well is really to decarbonize this industrial sector. So also for off-grid application, but we have also obviously on-grid application and also prospect of building new large nuclear reactor in Canada. Thanks, Sophie.
Thanks, Kathy. That was really interesting. I didn't know that uranium was first mined in Canada, so that is an interesting fact. Great. On that note, we've got our first question through, which is for David. So here we go. So where do you think the biggest advancements in nuclear fuels is going to come from? Will it be legacy OEMs, startups, or a mixture of both? And how will we convince the regulator, and more importantly, the public that new fuels are the way to go? And could you also explain what OEMs are for our audience as well?
Yeah, no problem. So I think OEMs, I guess, in the context is original equipment manufacturers, but as people may be aware, you can have fuel from other vendors in different reactors. So I guess in the context, it's the big players such as Westinghouse in the market. This question is that I think the question is interesting, and I was just thinking then that actually when we think about reactors that are being built today of the current type that we've just been speaking about, generally that sort of metallic cladding with uranium dioxide fuel, they are actually going to be operating for many decades, possibly based on lifetime extension, 60 to 80 years. And some of them haven't even started operating yet, so they're going to be operating well beyond my life expectancy, which is really impressive. So there's going to be innovation within that fuel undoubtedly over time, but it builds on the many decades of experience of operating safe and secure low carbon generation through that type of reactor. So I think what we see in the industry is a lot of collaboration between national labs, universities to bring innovation, and so that's something we do as an organisation to make sure that we are getting the input from many to do that and help us innovate. So I think we will see probably a mixture. Picking up on the second part about will the advancement come from startups? I think there is obviously a lot of interest in nuclear worldwide, a lot of startups, and some of them have fuel cycles which are very similar to what we see today, and others are completely different. Clearly, as the question implies, that's got to get regulatory confidence that it's going to be safe to operate and build on a lab scale experience or whatever operating history we've got. So I think in the short term, we will see the innovation to continue within as the question's worded in the OEM but the big players. But actually over time, as that assurance builds, maybe there will be more there. But I think it will be a mixture. Having a mixture of different vendors is healthy as well in terms of that from a diversity perspective.
Thanks, David. Got another question come through for Dave. So how do fuel requirements change for the scale of nuclear reactor? So for example, with micro reactors or small modular reactors to large scale reactors?
Yeah, so part of the answer to that is the blindingly obvious, which is that the amount of fuel you need to put into the reactor changes quite significantly, whether it's for a micro reactor or a large reactor, and the refueling frequency as well. So that's perhaps just stating the obvious. Obviously, with the UK policy at the moment, we have policy for large scale reactors. The sort of gigawatt scale would be based on light water reactors, and also competition at the moment looking at small modular reactors, which would be based on similar technology, so that we can consider really the fuel requirements for those two classes to be quite similar. And as David sort of described, largely around uranium dioxide fuel in a zircaloy cladding. For these smaller reactors, this is where we're starting to look at generation 4 systems, and the UK's gone through an exercise looking at which of those, if like, advanced modular reactors are most applicable to the UK needs, and that exercise came out with the high temperature gas reactor as the most favoured option. So a lot of micro reactors are indeed based on high temperature gas reactor technology, and using, as Kathy mentioned, this stuff called triso-fuel, tri-structural isotropic. So that really to the idea of fuel manufacture on its head, in that we go away from the idea of having lots of pellets of fuel clad in a tube of metallic tube, and actually getting rid of the cladding and having individual particles or kernels of the fissile material, and then cladding them individually in their own sort of multiple layers of protection. So it changes the way the cladding is applied. And these particles, these triso particles, are no more than 0.5 millimeter in diameter, so about the size of a poppy seed. And you can imagine each of those has got its own protective shield around it, and they are then put into compacts or pebbles, depending on the design. So for those types of reactors, the requirements are very different for the fuel manufacturer, and it's something we're working on at NNL, is establishing a pilot scale capability for manufacturing these triso fuel particles, and for us, it's a different technology, and it has quite a different requirement for the people who are researching it, and also for ultimately for the manufacturing processes that would go into making that type of fuel.
Thanks, Dave. So I guess as well, with the more novel technology with the triso fuels, obviously that question of how to prove it to the regulator as well is potentially another thing to think about on that as well.
Absolutely. I mean, you touch on the regulatory role in this. Fuel isn't licensed individually; it's licensed as part of a reactor. So when the reactor operator goes to the regulators to get approval for siting and operating a new reactor, they have to justify the claims around the fuel. So the two things are linked. It's always important that the fuel is properly tested, and we have acquire evidence for its performance, not just in its normal operating conditions, but as Phyllis said, in those abnormal conditions as well. So developing strategies around irradiation, testing, using international facilities for materials test reactors to prove the function of the fuel is going to perform as it's predicted in models, etc., is a really important aspect of fuel development.
Thanks, Dave. Our next question, I'm first going to ask to David. So what do you see as the biggest barrier to commercializing advanced fuels in the UK?
I guess just maybe split the answer to two. If we talk about advanced fuels and sort of continuous innovation in reactors that perhaps we have experience of today, as Dave's mentioned there, we can try things out in test reactors offline, which builds confidence, and then we'd look to do lead test rods where you have individual rods or lead assemblies where you can test things out and build that assurance and confidence that you've got a robust safety case for that fuel to operate on a larger scale. So in that case, it's a very clear path, and actually generally the disposition of the product when it's being used is understood in terms of the spent fuel and how you manage that, because there's a lot of effort being studied on uranium dioxide fuels. Anything likely in that area is going to be incremental. When we start talking about some of the more advanced fuels, to me, I think the biggest barrier is probably actually understanding the full fuel cycle and the work needed to understand how you manage the spent fuel. That's where once you've actually decided what that advanced fuels look like, you need to invest in that, because when you look worldwide at the amount of research efforts into UO2, which is actually very stable in the spent fuel state as well, even without doing anything with it, is something that needs to be understood, such that you can then get the confidence you've got a full fuel cycle to get the regulatory approval to be able to operate that fuel cycle. So yeah, it's having that full fuel cycle which will probably slow the development of some of the more advanced designs.
Thanks, David. And Kathy, the question was related to the barriers in the UK, but I was just wondering if there was any that you see that differ in Canada.
Yes, so rather than saying barrier, I would prefer say that this implementing new technology and new nuclear fuel in advanced reactor is a process which very regulated, very thorough in the demonstration that what you want to put in a reactor in the interior system in specific condition is safe. So I will say that the process itself to demonstrate that and give the confidence to the regulator that all anticipated situation will be handled correctly, and the fuel will perform as we expect it to perform in all anticipated conditions, normal or abnormal, as Phyllis also mentioned. That takes time. It's not necessarily a barrier, it's just that the process is fairly long. And I will say that more specifically for Canada, we are fortunate to have a dedicated type of technology here in operation in our current fleet, which is a CANDU reactor, Canadian Nuclear Deuterium Uranium technology, which doesn't operate using enriched fuel, but natural fuel. And we used a moderator, which is called heavy water. So it's another type of means to develop a technology. And for all those advanced reactor we are talking about here in advanced fuel, they required slightly increase of the fissile materials in those reactors. So for Canada, which is not a country where we have enrichment capability, that is a challenge, access to this type of fuel, which are very much aware and discussed at the highest level, and all the industry and all the sector is looking into different options for having access to this fuel for future reactor. But it's very specific to Canada.
Thanks, Kathy. That was really interesting. I'm going to throw out to a quick question, but it's quite a broad one. So before we go to another question to our audience. So this one's to Dave. The government is targeting net zero by 2050. What are the timescales for these future fuels, and will they be ready for deployment in time to contribute to these net zero targets?
Yeah, great question. It's all about the pace, isn't it, at which we can introduce new technologies. And I think it'll depend on different aspects. We talked a little bit about things like coated cladding. That's already lead test rods, lead test assembly sort of position now. So I think that something like that is an improvement for existing light water reactors is on the cards in fairly quick time. The things like the TRISO fuel I mentioned for high temperature gas reactors, there is more work to do. We've been doing some work with government on this, sort of looking at the timelines for deployment. They've got an ambition to have a demonstrator reactor in the early 2030s, and I think it is achievable for the fuel side to be developing the fuel manufacturing processes to be able to make the fuel in time to put into a demonstrator for the early 2030s. So it's quite an accelerated time frame, but I think we have I believe building up the expertise to be able to do that. And in parallel, there is obviously the question about qualification of fuel, and that can run in parallel with developing the capacity to manufacture the fuel. And so there are timelines associated with that, but also a lot of other countries are in the same position as the UK. And there's a lot of activities, for example, at the Nuclear Energy Agency, looking at how do we accelerate fuel qualification timeframes. So can we not always take 20 years to develop and implement a new fuel? Can we do it in 10 years or less? And that sort of then frames the challenge for us. Otherwise, it will be too late for nuclear. We will not be able to contribute to these net zero targets. So there is a challenge on the industry to find ways to accelerate its cycle of innovation and development.
Thanks, Dave. Yeah, I think that's the really interesting point, is that the net zero targets are for 2050, and we really do need to advance where we can. But the world doesn't stop at 2050, and having a long-term plan afterwards is also important. So yeah, thank you very much. On that note, we're going to go to a question to our audience then. And that's appearing on your screens. And that is, what do you think is the most important aspect of innovation in fuel design and manufacture? So we've got 3 options for you on this one as well. So do you think designing for maximum energy production, so getting the most out of your buck that you're putting into making the fuel in the first place, designing fuel that is more robust and resilient, so talking on those same lines that Phyllis was mentioning about the buzzword of accident tolerant fuel, or making fuel that can be recycled? Let's see when the answers come in. Which is your favorite, or what you think is the most important aspect? Okay, so interestingly, making fuel that can be recycled. Does anyone from our panel want to discuss on that? I mean, it's obviously a very important thing in terms of a long-term strategy of what we do. Oh, that's gone slightly down with more answers, but anyone want to throw in their thoughts? Go on, Dave.
Sorry, I put myself on mute. Just sort of jump in and say a little bit, obviously, about recycling of fuel. And the UK has in the past had a policy to reprocess spent fuel, but we are now in a position where we're effectively in an open fuel cycle position. That doesn't mean to say we can't come back to it in due course. And I think there's a lot of options there for fuel to close the fuel cycle. You can do that through adding plutonium, which is obviously a product of from the reactor, back into making new fuel with mixed oxide fuel. And that mixed oxide fuel can also use depleted uranium, which is a byproduct of the front end of the fuel cycle. So mixed oxide fuels is one way of doing it, or actually going into fast reactor fuel cycles. And then again, the UK has a fantastic legacy and history in doing that. An entire program at Dounreay, we got to the point of pretty much having a first of a kind of a sodium cooled fast reactor developed, but wasn't taken forward. So there are a lot of options there in terms of closing fuel cycles in the future. So I think it's really interesting that people on the call here are seeing that as important to them, and I think it's also important that we do maintain research programs that are looking at those sort of fast reactor fuel materials, because it's so easy that you lose that capability if you don't maintain expertise through research and development programs. The Dounreay program sort of came to a halt in the early 90s, and so that's a generation ago now. And so we've got to be careful and ensure that sort of investment, that we are always looking into that longer term future for nuclear as well.
Thanks there, Dave. So we've got another question in from our audience that I want to ask to Phyllis. So when considering the deployment of new reactors that use alternative fuels to the traditional UO2 or uranium dioxide, is it important to consider the complete fuel cycle? What do the panel consider the most significant challenges associated with developing a fuel cycle for a fuel such as TRISO?
Right. I think it's really important to make sure that the fuel hits the notes on maximum energy production, and also that improvement also in robustness and resilience, and also those recycling aspects are also important. So this is the headaches that engineers have to deal with all the time. Oh, not headaches, but good challenges. So where you apply optimization approaches on there. And just also for this, for the tiny fuels that David and Kathy have already described and explained on, which are the TRISO fuels. I think just making sure that both from the manufacturing point of view, processing point of view, to the performance, and also considering the recycling aspects is important, because what you want to have is also for to get it on environmental aspects for recycling, and also recycling helps to increase that efficiency in the system. So you're really talking about increasing the benefits when you look at the cost benefit analysis.
Thank you, Phyllis. Yeah, so oh, sorry, Dave, would you?
Just add on to Phyllis's answer. With the TRISO, I would just sort of say it's what we call the head end part of the reprocessing facility, which is the part where you try and deconsolidate and get to the uranium. Obviously, with the TRISO material, you've made it so resilient by putting all these layers on it. It's harder to get at the uranium and then extract it and leach it out, but there are technologies in place to do that, sort of electrochemical based sort of deconsolidation. There's something we've been looking at with the University of Manchester, looking at high voltage discharges. A number of things have been tried in the past. I think the challenge is actually to develop those processes and to make them economic, because ultimately it'll be an economic decision as well, with the value of the recycled material versus the challenge, the technological challenge of doing the reprocessing activity.
Thank you, Dave. So yes, I guess that under slightly changing the material science and chemistry of the system in one aspect can sometimes have new challenges in other areas, that, as you said, in the recycling. Really interesting. So I have another question. This one's for Kathy. So on to TRISO fuels again. So many of the nuclear fuels, such as TRISO, have advantages when operating in a nuclear reactor. But how is the full life cycle assessment from cradle to grave taken account for? This includes mining, decommissioning, and long-term disposal.
Yeah, so Dave touched a bit onto that, right? TRISO fuel is considered as the most robust fuel on Earth. That is a famous quote from the US DOE, I believe. So yeah, it's so robust that you have to come up with technology to deconsolidate it, like Dave mentioned, and if we want to look at diminishing the radiotoxicity of the waste as well, considering the recycling of those tiny particles is also something to look at in terms of diminishing the high level radioactive waste and also reusing valuable material that wouldn't have been used during the first cycle of the fuel. And how all that is taken into account? Well, it's during the process of a new technology and new reactor licensing. There is a consideration also on how the waste generated from this new reactor will be taken into account. So very much before the construction, the designer has to demonstrate that there is a plan for handling the waste generated by this new reactor. Yeah.
Thank you, Kathy. Our next question is for Phyllis. So again, still on the TRISO fuel. So TRISO fuel reactors, TRISO fueled reactor fuel has many layers. Does this lead to an effective thermal conductivity? Does the thermal conductivity reduce with operational time in a reactor? And the TRISO fuel pellet also builds up with fission gas during operation. Does this become a limiting factor in terms of operational time?
Great one, Sophie. I must say, TRISO fuels, they really shine in terms of the surface area to volume ratio. So their size, because they're really tiny particles, really the size of a poppy seed, that's the size of one TRISO particle. So this surface area is important in enhancing thermal conductivity because heat transfer is influenced by area. So that's where TRISO particles shine in terms of thermal conductivity. However, the layers have great advantages and benefits that they bring to the fuel. The primary one being robustness. That is the main concept of having 3 layers and their composition really well designed for that, because during processing, if you were to apply a single coat, for example, to these tiny seed-sized fuels, you'd find that there's the risk of the coating getting compromised if during processing or during handling. So having these 3 layers is important. There are also other approaches to not having 3 layers. There are also approaches to having just 2. And there's also research on looking at just one coating, for example, metal coatings on the particles, which may enhance the thermal conductivity from the coating point of view. But what is also important about these TRISO fuels is that they have the capacity to store fission products in the layers. So because these products are generated as the fuel is being used in the reactor, they tend to want to sneak into spaces, and you don't want these products to sneak into the main fuel. You'd rather channel them out so that you'd rather have the coating accommodating them. And the beauty in the TRISO coatings is that the materials are designed, for example, the buffer layer you'd put is well designed to have nice spaces or pockets that can store these fission products. So I think TRISO really shines in different perspectives when you look at it. So some of the limitations are overcome by the advantages. So it's a nice balancing act, really.
Thanks. Yeah, so Phyllis, when you mentioned that one pro is the fission products are contained within the layers rather than escaping to parts in the reactor that might be hard to get to, is it then easy to get those fission products out at the back end if our triso fuels are so robust?
Wow. That's a good question that you've thrown. I think we're going to channel the question to research. It's the kind of questions that we like considering when we're doing research. So, Sophie, I'm going to add that one to one of the things that we could look at. So if that's okay, I'll add it to some of the questions we could answer on TRISO.
Yeah, that's absolutely fine. That's me going off piece and just being interested. I'm excited if you do look into that in the future. Right, on to our next question then. So I'm going to start with Dave and then pass this over to Kathy as well. What is your opinion on a closed loop fuel cycle?
So if I go first, I've kind of sort of touched on this earlier, really, in terms of how we close the fuel cycle. We don't have that currently in government policy, but I think it is something that will come back around in due course. Exactly when is difficult to say, because it maybe, you know, it's an economic argument there. It's also just about managing our waste appropriately. So I think there's, my opinion is that we should be looking at this. We should be continuing our research into things like mixed oxide fuel development, as well as fast reactor fuels, so that when that time comes, we have got the necessary skills and expertise to start to deploy our own, our field expertise, so that we can continue what we said right at the start of this, about having domestic supply of all types of fuels for all types of reactors.
Yeah, and sorry, Sophie, I thought
Sorry, I was just going to pass over to you.
Yeah.
Kathy, please go. Yeah.
Yeah. So really, it's I have a similar position than Dave on that. From the Canadian perspective, we don't currently have a policy to close a fuel cycle here, but the same, we also have a program to look at the research and development for processes that we could use for doing so, and what is important is, as been mentioned earlier in the discussion, was to really use and reuse at the maximum all the valuable material which is in the fuel after one cycle, because a lot of fissile material, valuable materials, are still yet to be burned and used. So if we look from the perspective of sustainability, it's critical. And I also mentioned earlier that from the perspective of decreasing the radiotoxicity of waste, is also it's also a key to close the fuel cycle here, in my opinion. And I know that it's waste is one hot topic for the public acceptance, and legitimately so. So for this consideration, I think, is critical as well to consider and do the research to be ready to close the fuel cycle.
Thanks, Kathy. Yeah, as we had in our voting, recycled fuel was one of the top things, so it's obviously an interest to our audience. And then I'm going to try and get in one last question, and this one's for David. So, is there a chance for thorium to replace uranium in terms of fuels, and how advanced is research and technology regarding nuclear safety, handling, and storage?
Okay, so I guess the question would be is what problem we're trying to fix. And at the moment, uranium availability, when you look at the forecast, is pretty good, and there's a lot in a different range of countries, albeit most of it's, with the exception of Canada, is not in the countries that generally generate a lot of nuclear power. But it's quite once, and there's a lot of exploration going on. Thorium reserves are quite abundant in the world, but probably more limited geographically. There has been research done in many countries, and some countries have been actually looking at it. And if you look at the IEA as well, in terms of they set up the standards for safety, they have issued papers on the past. I can't really do justice in the time. I think the other thing I would just add is that thorium fuel cycles are more complicated because unlike uranium-235, where it just sort of works on its own, there's a lot more needed there. So it's a mixture of things that need to be in there. So I think it's something that will probably get more research time over the coming decades, and particularly of the countries probably that have got the abundant resources of thorium. It'd be daft for them not to look at it. But perhaps in the context we're looking in the UK, I think we'll probably and other areas sticking with uranium for now, but certainly not something we wouldn't rule out.
Thanks, David. Now, unfortunately, I'm really sad to say we're almost out of time. So what we want to kind of leave with is asking one final question to our audience. So we're going to produce what's called a word cloud. So if you could tell us what is the most interesting, exciting, or surprising word that you're going to take away from this webcast, in the same manner that you've done with the questions, we'll start to pull that together. But whilst we wait for your responses, I'm going to ask our panel if there's one key message you'd like our audience to go away with, what would that be? So I'm going to start with Dave.
So from my perspective, I think this is an exciting time to be a nuclear fuel specialist in the UK. Fuel technology is on an upward trajectory, in my view. There's lots of opportunities in the future, and it's essential to our fuel security, energy security. So those two things go hand in hand. If we want to have proper energy security in the UK, we need to have fuel supply in the UK. And that's it needs an investment. It needs us to work and come up with innovative solutions to some of the challenges that we'll be facing in the future. But what a great time to be working in nuclear fuels.
Thanks, Dave. David, what would be your message?
Yeah, I agree fully with what Dave said. I think it's a great time. I'm very excited. I've worked in the industry over 25 years, and there's a lot going on. I think the potential for growth. And I think I reflect back, and we've got nearly 80 years worth of experience of fuel cycle in the UK. Many years of reactor operation, and actually building on that history, and also looking at some of the stuff that we are looking now historically. So there's a lot of sort of great provenance and I think hope for the future to actually move fuel cycles forward and be really innovative in that. But remembering the fact, as I said, a lot of the stuff that we're building today will operate for many decades, and it'll be built on the safe and secure technology that we've been using for the decades previously. So there's a lot of stability, but also a lot of innovation to be had, I think.
Thanks, David. Kathy, what would be your message?
Yeah, in addition to what Dave and David mentioned about the exciting time for a fuel expert here to have the opportunity to look at and doing research on different type of fuel, really very diverse in terms of structure and application and usage. I would say that for me, it's nuclear energy is one important consideration to combat climate change and meet our zero emission targets. And whichever way we manage to do that in our country, that will involve looking at fuel. And that is very exciting to be part of the solution from this perspective, and also obviously the consideration on energy supply security as well, involved knowing how to make fuel domestically or with a like-minded country is key there. And now there's great time to be in this industry.
Thanks, Kathy. And then Phyllis, what would you like your message to be?
Sophie, I think it's great to see how the nuclear industry has been growing bigger and how the future looks bolder and brighter. I can only echo what Dave, and Kathy have already said. And also, just to say, nuclear energy is such star performer. Although there's still a lot of, as it is growing, there's still more questions that are coming up that need to be answered, more solutions and more innovative and the ideas coming up. And I can say to the audience, the nuclear industry needs you. It needs your skills. Sign up.
Thank you, Phyllis, and thank you to all of our panelists. I'm excited to try and get involved in some more fuel design projects if I can now. I've had a very exciting hour, and I hope our audience have too. I guess just to comment on the one word that seems to be the biggest word cloud. Obviously, one takeaway message is the interest in TRISO fuel and recycling. And clearly poppy seed has come up a couple of times as well, so everyone has the right idea when they're thinking about TRISO fuel in their heads. Yeah, we end. Is there any other comments our panel would like to share in relation to this word cloud? Apart from that fact that TRISO is clearly out there.
The only thing I'd say is that TRISO is an acronym that's obviously been embedded in our knowledge. It's tristructural isotropic, but it doesn't actually describe what it is. So we tended to use coated particle fuels and leave people with that thought about how do we describe these things, because TRISO is a bit complicated as a description. But there we are. It's good to see those words coming through.
Yeah.
Thanks, Dave.
And maybe can say long live TRISO, live coated fuel. It's just great to see that. Yeah.
Definitely. What a great note to end on there, Phyllis. Yeah, so just thank you again for everyone who has joined our series today. This is the second in the series, and we're keen to see what your thoughts and opinions are and see if we can improve where we can in the future. So a short feedback form should be sent. There's a link going out, so we'd be really grateful if you can answer that. That will help with our future podcasts. And we're really looking forward to seeing you at the next one. Thank you again to our panelists, and thank you all for listening. Thank you.